Hello and welcome to the Sleepy Narrator. Tonight we are drifting into a calm yet curious corner of nature, the strange and surprising ways animals sleep. From creatures that nap while flying to those that hardly sleep at all, this is a world filled with unusual adaptations and quiet mysteries. Before we begin, I would love to know where you are listening from tonight. If you enjoy gentle science stories like this, a soft reminder to give the video a like and subscribe so you can join future explorations. And for those already subscribed, thank you. Your support keeps these quiet journeys alive. I will try not to make this so fascinating that you lie awake, eyes wide, thinking over every fact. But if that happens, at least you will wake with a head full of strange animal trivia. So, what does it look like when a creature with no brain falls asleep? Rest is one of nature's quiet marvels, a state where the body seems to switch off, but internal rhythms continue their hidden work. At its simplest, it divides into two primary forms: rapid eye movement sleep, or REM, and non-rapid eye movement sleep, often shortened to non-REM. In humans, REM is when our most vivid dreams appear, with the eyes darting beneath closed lids and the brain showing activity nearly as lively as wakefulness. Non-REM, on the other hand, is calmer, marked by slow breathing, steady heartbeats, and sweeping electrical waves across the brain. These two conditions alternate through the night like a delicate dance between stillness and activity. For humans, a full cycle lasts about 90 minutes, though this varies across species. Some animals pass through the stages in mere minutes, while others stretch them for hours. Cats, for example, enter REM much sooner than humans. Certain marine mammals drift in and out of lighter non-REM states, never allowing both halves of their brain to surrender at once. At the center of sleep lies the circadian rhythm, an internal clock present in nearly all living beings, keeping time with the rotation of the Earth. In humans, this rhythm is guided by a cluster of neurons called the suprachiasmatic nucleus, located just above where the optic nerves intersect. It responds to light from the outside world to adjust our biological schedule. As daylight fades, the pineal gland releases melatonin, a hormone that signals the body toward rest. With the return of morning light, melatonin drops and wakefulness rises. In animals, this system can be similar or very different depending on whether they are nocturnal, active in daylight, or following bursts of activity through both day and night. Brain activity during rest is far from uniform. In non-REM stages, especially the deepest phases, neurons fire in slow, synchronized waves like tides rolling on shore. This slow-wave sleep seems to be a period of repair. Muscles heal from strain, the immune system strengthens defenses, and the brain clears out metabolic waste. REM, by contrast, is vivid and unpredictable. Neurons fire rapidly, brain temperature increases, and regions tied to memory and emotions light up with patterns suggesting intense inner activity. Meanwhile, the body is paralyzed from the neck down, a state known as atonia. This safeguard prevents dreamers from acting out their visions, whether it is a person, a dog dreaming of chasing a ball, or a cat lost in an imagined hunt. What makes this remarkable is the variety across species. Some spend half their lives in slumber, others hardly touch it. Certain reptiles show rest states resembling REM, blurring the once clear line that set higher mammals apart. Cephalopods such as octopuses enter colorful twitching phases that may represent their own version of dream sleep. In every case, sleep is more than rest. It is a shifting tapestry of signals, hormones, and rhythms. Each stage plays its role. Like ocean tides, brain waves ebb and flow, carrying the sleeper through deep stillness and into vivid REM before returning again. Despite being familiar, sleep remains an uncharted frontier, one every creature navigates in its own way. When we close our eyes, our bodies cycle through stages as old as life itself. Broadly, these stages fall into two categories: REM and non-REM. Non-REM generally comes first. In lighter forms, the body relaxes, breathing steadies, and heartbeat slows. Muscles can still move, and the mind drifts toward soft thought rather than dream imagery. As deeper levels arrive, the brain's activity slows and synchronizes, producing large sweeping waves that give slow wave sleep its name. This stage restores the body, repairing tissues, producing growth hormones and bolstering immunity. REM is more dynamic. The eyes dart beneath lids, breathing becomes uneven, and heartbeat quickens. The body's voluntary muscles are paralyzed in atonia, preventing action during dreams. It is in this phase that the most vivid dreamscapes appear. Other species experience similar phenomena in their own ways. Brain scans reveal that during REM, regions linked to memory, learning, and emotions ignite with activity, suggesting REM helps process the day's events. The alternation between non-REM and REM forms a cycle. In humans, each cycle is about 90 minutes and repeats several times through the night. Other creatures follow very different schedules. A cat may fall into REM within minutes of lying down, while marine mammals cycle in ways that keep half their brain awake. These variations reveal sleep's flexibility. The foundation is ancient, but timing adapts to each species' needs. Beneath it all lies the circadian rhythm, the body's inner clock. In humans, this rhythm is governed by the suprachiasmatic nucleus. Light serves as its metronome. As evening arrives, melatonin rises, nudging toward rest. With sunrise, melatonin falls, opening the way for alertness. This cycle is not unique to humans. Nearly every organism has a daily rhythm, from flowers opening at dawn to nocturnal creatures stirring at dusk. For many, rhythms are guided not just by light but by tides, temperature, and seasons. In the wild, rest is less about clocks and more about tuning to environmental cycles. The brain's electrical patterns during rest are especially fascinating. In deep non-REM, neurons fire in slow, rolling waves like swells of the sea. These waves seem essential for consolidating memory and clearing waste. In REM, those calm surges give way to bursts of activity, resembling wakefulness but untethered from senses. These bursts produce the vivid, often illogical sequences we call dreams. While humans are the common reference, other animals display extraordinary variation. Horses and giraffes spend far less time in REM than humans. Some birds have REM so brief it flickers like sparks. Certain reptiles show REM-like states, overturning the belief that dreams belong only to mammals and birds. Octopuses display rapid skin pattern changes in active sleep, suggesting vivid internal experiences. What unites them all is a rhythm of alternating activity and rest within the brain. In both the slow surges of non-REM and the bursts of REM, the brain is never idle. It consolidates memory, repairs cells, and possibly dreams. Like the rhythm of tides, brain waves ebb and flow, carrying sleepers through the cycles of the night. Why we sleep has puzzled scientists for centuries. At first glance, lying still for hours seems a poor evolutionary strategy. Yet nearly every animal on Earth rests in some form, from humans and whales to insects and even creatures without brains. Sleep must serve something vital. One explanation is the energy conservation theory. Rest lowers the body's demand for fuel during times when searching for food is less efficient or more dangerous. In humans and many animals, body temperature drops slightly during sleep. Metabolism slows and energy is conserved. For early creatures, sleeping during the coldest, darkest hours meant burning fewer calories and avoiding unseen dangers. Even today, this nightly dip suggests sleep is a way of saving resources. But the benefits go further than conserving energy. One of the most vital roles lies in memory and learning. During REM and deep non-REM, the brain replays and organizes the day's experiences. In experiments, rats trained to run mazes show brain activity in sleep that mirrors the patterns recorded while navigating. It is as if the brain rehearses the task, strengthening connections for memory. Songbirds show similar evidence. They practice tunes in the day, then during rest, brain activity resembles singing, as though refining songs in silence. Without enough rest, learning slows and memory falters, a truth shared across mammals, birds, and possibly reptiles. Sleep is also a period for repair and immune defense. In deep non-REM, the body releases growth hormone, aiding in muscle and tissue repair. The immune system increases production of proteins that fight infection and inflammation. Scientists have even discovered that the brain has a cleansing system, the glymphatic system, which flushes out waste like proteins linked to diseases. This system is most active during deep sleep, suggesting that without rest, harmful substances could build up. Of course, in nature, rest carries risks. Predator avoidance theories propose that the timing and depth of sleep are shaped by the need for safety. Prey animals often sleep lightly or in short bursts to stay alert. Grazers like deer or horses rarely rest deeply for long, instead taking many short naps across day and night. Predators, facing fewer threats, often enjoy longer, deeper sleep. Lions may rest over 20 hours a day when food is abundant. In both predators and prey, sleep is a balance between restoration and vigilance. To understand the origins of sleep, we must look deep into evolution, and surprisingly, the trail leads to creatures without brains. Jellyfish such as Cassiopeia, the upside-down jellyfish, show clear signs of rest. At night, they pulse less and respond more slowly to disturbance. If kept active during usual rest periods, they grow sluggish the next day. This suggests even jellyfish need recovery. Remarkably, they have no central brain, only a nerve net. The fact that jellyfish, creatures that split from other animal lineages hundreds of millions of years ago, seem to sleep suggests that rest did not arise with complex nervous systems. Instead, it may be one of the oldest behaviors in the animal kingdom, emerging as a way to match activity with environmental cycles. Over time, as nervous systems grew more complex, this basic rest evolved into the multi-stage sleep seen in mammals, birds, and other advanced creatures. Sleep may never have had a single purpose. Instead, it is a bundle of processes, conserving energy, sharpening memory, repairing tissues, strengthening defenses, reducing risks, and with origins so deep that even brainless animals share in it. Far from being a weakness, rest is one of life's most enduring rhythms, a nightly reminder that sometimes the best way to survive is to be still. For most of us, rest is an all-or-nothing experience. We lie down, close our eyes, and let the entire brain drift together. But in open oceans, high skies, and windswept lakes, some animals have mastered a trick that looks almost magical. They sleep with only half their brain at a time. The other half stays alert, ready for action. This unusual ability is called unihemispheric slow-wave sleep. It is the ocean's version of keeping one eye open, except that eye may be watching for sharks, rival pods, or sudden storms. Dolphins are perhaps the most famous practitioners. Unlike humans, they cannot rely on unconscious breathing to stay alive. Every breath must be taken deliberately, and forgetting to surface would be fatal. Unihemispheric slow-wave sleep solves this. When the left half of the brain rests, the right half remains alert enough to keep the dolphin swimming slowly and surfacing to breathe. The right eye, connected to the left hemisphere, stays closed, while the left eye, linked to the active hemisphere, stays open, scanning for threats. After some time, the hemispheres trade roles, ensuring each gets deep rest without the whole body shutting down. Whales share this system, though on a grander scale. Sperm whales can rest vertically, their immense bodies hanging like pillars in the blue water, while others float beneath the surface in a behavior called logging, since they resemble drifting logs. In both cases, one hemisphere rests while the other manages breathing and awareness. Calves bring extra complexity. Young whales and dolphins need to breathe more often and stay near their mothers. Mothers swim continuously in the early weeks, guiding calves through rolling wakefulness where neither is fully at rest. The skies hold their own half-brain sleepers. Migratory birds such as the great frigate bird can stay airborne for days or weeks without landing. These birds rest while gliding, dipping into short bouts of unihemispheric sleep lasting only seconds. One hemisphere rests while the other monitors balance, navigation, and the surrounding air. The open eye on the active side watches for companions, weather, and land. On the ground, unihemispheric sleep appears in roosting birds. Ducks resting in lines often display a neat system. Those in the middle close both eyes, while those on the edges keep the outward-facing eye open. As the group shifts, sentinels rotate, ensuring constant watch. The mechanics of this behavior are fascinating. In vertebrate brains, the hemispheres are connected by bundles of fibers that allow constant communication. In species capable of unihemispheric rest, the hemispheres can act more independently. When one enters slow-wave sleep, neurons fire in large synchronized waves, while the other maintains the faster patterns of wakefulness. Muscle tone stays intact because this is not REM sleep. The active hemisphere continues swimming, gliding, or guarding while the resting side recovers. The open eye is essential, since signals cross to the awake side, feeding it environmental information. In dolphins, the open eye often faces the pod, maintaining social contact. In birds, it usually faces outward, watching for danger. This is rest in its most efficient form, recovering without full vulnerability. Why did such a strange system evolve? For marine mammals, the answer is clear. Breathing must be actively managed, and oceans are full of hazards. A fully unconscious whale could sink too deep, drift into danger, or miss a predator. By alternating hemispheres, they never lose responsiveness. For migratory birds, the pressure comes from endless journeys. Crossing oceans or barren terrain leaves no safe landing. Sleeping while flying, even briefly, lets the brain recover without halting the journey. For roosting birds, keeping one eye open provides early warning of predators. This behavior appears in dolphins, whales, seals, ducks, and frigate birds, species with very different lives. It likely evolved multiple times, shaped by similar pressures. Nature, faced with the same problem, found the same solution in separate lineages. Whether in water or air, the challenge is the same: how to rest without becoming an easy target. Some seals show a remarkable twist. Fur seals sleep one hemisphere at a time while at sea, but when hauled out on land, they rest both hemispheres together like typical mammals. This flexible system shows just how adaptable rest can be. Humans, however, are wired differently. Both hemispheres usually rest together. At most, we may sleep lightly in new or unfamiliar places, a partial night watch. But it is nothing like the finely tuned system of these animals. For us, safety comes from shutting down completely. For dolphins or migratory birds, safety comes from never fully shutting down. Unihemispheric sleep challenges our very idea of slumber. It is not a single uniform state, but a flexible set of strategies. In some creatures, it is split neatly between hemispheres, turning rest into a balance between vulnerability and vigilance. In the hush of a moonlit ocean or the thin blue air above the sea, half a mind drifts in waves of rest, while the other half keeps steady, alert, and moving forward. For some animals, being half asleep is not restlessness but perfect adaptation. For most of us, a nap lasts minutes of quiet dozing. But in the animal kingdom, a nap can be shorter than a blink. Some species have mastered the art of sleeping in microbursts, mere seconds at a time, without losing survival grip. These are the masters of the micronap, making even the busiest humans seem lazy. One of the most astonishing examples comes from birds that travel for days without landing. The great frigate bird, champion of long-distance flight, spends weeks over open oceans where no perch exists. Fitted with tiny brainwave recorders, these birds were found to snatch rest in bursts, sometimes only seconds long. One hemisphere may slip into slow-wave sleep, or both may rest briefly if conditions are calm. The wings remain locked in a gliding position, riding air currents while the brain steals a flicker of recovery. Closer to shore, other birds also rely on micronaps. Swifts, known to spend months in the air, likely do the same. Their exact patterns remain under study, but they are believed to nap briefly while flying. The secret is efficiency. No landings, no extended vulnerability, just tiny sips of rest built into motion. The seas hold their own specialists. Seals and sea lions adapt their rest depending on land or water. On land, they sleep like typical mammals, with long stretches. At sea, however, they float vertically with noses above the surface, breathing without fully waking. Others alternate between naps while drifting and bursts of alertness to swim or dodge predators. These naps may last only minutes, sometimes broken into even smaller fragments. Sea lions catch bursts of rest while bobbing at the surface or in shallow waters. Why does such fragmented sleep work? For animals in high-risk or high-demand environments, micronaps are practical. By resting in many short bouts, they maintain constant readiness. A bird in flight cannot afford deep unconsciousness. A seal in open water cannot risk hours unaware. Micronaps offer the smallest windows of vulnerability while giving the brain recovery time. Over time, the total amount of slow-wave and REM-like sleep adds up, spread into fragments rather than a single block. Studying such short sleep is not easy. Scientists use tools like EEG to measure brain activity. Lightweight waterproof devices have been attached to wild birds and seals, paired with GPS and depth sensors. Frigate birds revealed brain activity showing mere seconds of rest mid-flight. Seals showed alternating naps depending on whether they drifted, floated, or swam. Motion sensors tracked wing beats or drifting positions to match physical stillness with brain signals. These findings challenge the belief that long, deep sleep is the only path to recovery. In the world of micronaps, survival depends on seconds, not hours. A frigate bird gliding over endless waves, a swift slicing through evening skies, a seal bobbing in water, each proves that rest does not need to be long to work. In places where danger never sleeps and the journey never stops, taking rest in small sips is the difference between thriving and failing. Far from compromise, micronapping is refined adaptation, showing nature's elegant efficiency. Where we see exhaustion, animals see opportunity, seizing brief moments of restoration before moving on. Dreaming remains one of sleep's most mysterious aspects. In humans, dreams bloom most vividly during REM, when brain activity mimics wakefulness. But dreams are not only ours. Across the animal world, many species enter REM-like states. While we cannot ask them what they see, their bodies give clues. In mammals, REM is widespread, though duration varies. Humans and primates spend a significant share in REM. Cats twitch their paws and ears, lost in imagined hunts. Dogs yip, paddle legs, and shift eyes beneath lids, replaying daily adventures. Rats show it even more clearly. Trained to run mazes, their brain-firing sequences repeat during REM, as though rehearsing routes in sleep. Birds too experience REM, though in shorter bursts. A pigeon's REM may last seconds, with eyes fluttering and head shifting, hinting at inner images. Songbirds show even stronger evidence. Zebra finches display brain activity during rest, mirroring the patterns used in singing. Researchers suspect they practice songs in dreams, refining melodies silently. Reptiles were once thought to lack REM, but studies on Australian lizards revealed alternating sleep states, one resembling REM. This suggests that dreamlike processes may be far older than once believed, stretching back hundreds of millions of years. In the ocean, cephalopods bring vivid displays. Octopuses and cuttlefish enter active sleep phases where skin patterns shift in rapid sequences. Pale one moment, boldly striped the next, as if reacting to imagined surroundings. Some scientists think these shifts reflect dream imagery, remembered hunts, passing predators, or the shifting light of reefs. The synchrony between skin changes and body movements makes the possibility compelling. Speculating about animal dreams is imagination grounded in evidence. A dog twitching may be chasing a rabbit. A songbird in REM may be rehearsing melodies. A rat may retrace tunnels. An octopus may drift over shells, its arms curling at dream prey. Even without human-like consciousness, the neural activity suggests these creatures inhabit inner spaces where past and present blur. Why dream at all? One theory is rehearsal, running simulations of challenges. Predators might refine hunting. Prey might practice escapes. Another idea is memory, organizing important experiences while discarding the rest. Either way, REM is active mental maintenance, shaped by evolution. The diversity of dreaming across species hints at deep evolutionary roots. REM-like states in mammals, birds, reptiles, and even cephalopods suggested arose long ago and persisted because it offered clear survival benefits. Whether for learning, memory, problem-solving, or emotional balance, dreaming proved valuable enough to last across vast evolutionary distances. In the end, animal dreams remain private worlds, glimpsed only through twitches, flutters, or color shifts. Yet these glimpses suggest something universal, that life needs not only to rest the body but to wander the mind's landscapes. In those quiet hours, paws run without touching ground, wings beat without leaving air, and skin flashes colors to seas that exist only in memory. If rest is a universal rhythm, then its forms are astonishingly varied. Some animals can go for months with little or no sleep, others nap constantly. The differences show just how flexible and inventive evolution can be. Among mammals, elephants stand out as some of the lightest sleepers. For such enormous creatures, they spend surprisingly little time at rest. Studies using GPS and movement sensors found that wild elephants in Africa may sleep as little as 2 hours a day, sometimes skipping an entire night. Unlike humans, they rarely lie down. Instead, they doze while standing, leaning against trees or shifting weight between legs. Lying flat is reserved for deep rest, usually only every few days. Even then, REM phases are short. The reason is partly lifestyle. Elephants must travel long distances for food and water. They are also constant targets of threats, including humans. For such vulnerable giants, long stretches of unconsciousness would be too risky. Bats, on the other hand, are near opposites. Some species spend up to 20 hours a day asleep. Hanging in caves or hollow trees, they conserve energy and avoid predators. Their diets of insects or fruit require bursts of activity, followed by long recovery. Since they are nocturnal, most of their daylight hours are spent clinging upside down in torpor. These extremes highlight how sleep is molded by need, not size or intelligence. Giraffes, like elephants, also sleep very little. In the wild, they average less than 2 hours daily, usually in short bursts lasting only minutes. Lying down with their long necks folded is rare. Most often, they rest standing, keeping ears flicking for sounds. On the other side, small animals like rodents or shrews can sleep more than half the day. Their fast metabolisms demand constant feeding, but their bodies also need long recovery. Laboratory mice, for example, spend about 14 hours daily asleep, much of it in deep non-REM. The contrast shows that there is no universal formula. Sleep balances energy, safety, memory, and biology differently for each species. Marine mammals bring another layer of complexity. Dolphins and whales rest half their brains at a time, as we saw earlier. But what about those that dive deep, like sperm whales? These massive creatures have been filmed hanging vertically in groups, motionless for minutes. They drift like silent pillars, half brains slumbering while bodies float. Such images reveal how even ocean giants must bow to rest, though in forms far from our own. Migration adds further challenges. Certain species travel such long distances that they cannot stop for traditional rest. Bar-tailed godwits, for instance, fly non-stop for over 7,000 miles across oceans. During these journeys, they rely on short naps, both hemispheres switching rapidly between wake and rest. When they finally land, they may catch up with long hours of deep sleep. The Arctic tern travels even farther, over 40,000 miles annually. It too must rely on fragmented sleep, woven into its journey. In extreme cases, animals nearly suspend sleep during key periods, a state called sleep suppression. Male pectoral sandpipers during mating season may remain almost continuously awake for weeks while competing for mates. Astonishingly, they show little immediate cost. Only later, once the season ends, do they compensate with longer recovery. How do they endure such deprivation without collapse? One answer may lie in the ability to recover efficiency. Even brief rests can provide restoration if timed with precision. In these cases, sleep is not lost but reshaped, condensed, fragmented, or postponed to suit survival. This theme appears across species. Seals at sea nap while drifting, but once ashore, they repay the debt with long stretches. Birds returning from migration also show rebound sleep. The flexibility is remarkable. While humans falter with missed nights, many animals simply bend the rules. Yet even they cannot escape the need entirely. Jellyfish slow their pulsing at night, evidence of basic rest. Fruit flies deprived of sleep later compensate with extra. When rats are forced to remain awake indefinitely, they eventually die. Sleep may be shaped in countless ways, but it is never fully erased. Its necessity seems as deep as breathing or eating. Dreaming, too, carries costs when missed. Rats deprived of REM show impaired learning. Humans experience irritability, memory lapses, and hallucinations. Birds deprived of REM sing poorly, their songs slurred and inconsistent. Across the tree of life, sleep debt leaves its mark. The form can vary, but the need remains absolute. The strangeness deepens when we look at animals that hibernate. Hibernation is often confused with sleep, but the two are not the same. In hibernation, animals such as bears, ground squirrels, and bats enter a state of torpor, slowing body temperature, metabolism, and heartbeat dramatically. A ground squirrel may drop its body temperature close to freezing, surviving months with little food. But during these long torpor periods, they still experience short episodes of normal sleep. Every few weeks, hibernating mammals warm themselves and enter true non-REM or REM before sinking back down. This suggests that even deep torpor cannot replace sleep's functions. Something unique happens during real sleep that hibernation alone cannot provide. Consider bears, the most iconic hibernators. They do not cool as much as rodents but can remain in dens for months with heartbeats slowed and metabolism lowered. While they rest deeply, they also stir, adjust positions, and likely pass through lighter sleep phases. Their slumber is closer to dormancy than full hibernation, yet it preserves energy through harsh winters. Migrating birds provide another version, torpor on demand. Hummingbirds can drop their metabolism each night to survive when food is scarce, entering a miniature hibernation. Bats do the same, hanging cold and motionless for hours. These flexible states show how rest and energy conservation intertwine. Extreme environments push the boundaries further. In the Arctic, animals face months of darkness or light. Circadian rhythms that rely on day and night must adapt. Caribou, for instance, lose strong daily rhythms in summer and winter, instead sleeping in scattered bouts throughout the day. Their rest aligns more with feeding than light cycles. Penguins in polar colonies also adjust. In endless daylight, they take hundreds of short naps, each lasting minutes, spread through day and night. Marine life faces different challenges. Deep-sea fish live in darkness year-round. Their rhythms follow food availability or ocean currents rather than sunlight. In caves, blind fish have lost circadian control entirely, drifting between activity and rest without clear cycles. The flexibility of these patterns underlines sleep's importance. Life bends it to fit every environment, but never discards it entirely. From desert rodents burrowing into cool sand, to bats clinging in caves, to whales hanging like statues in oceans, each has crafted a unique balance. Even in insects, patterns are clear. Bees rest with heads drooping and antennae still. Sleep-deprived bees struggle with navigation, unable to return to hives. Fruit flies, despite tiny brains, show REM-like activity and rebound when deprived. This suggests the roots of sleep stretch far back in evolution. We are left with a puzzle. Sleep is universal and vital, yet endlessly flexible. Elephants with 2 hours, bats with 20, birds that nap while flying, whales that rest half their brains. Each example reveals that sleep is not a single design but a toolkit, customized for each life. And the mysteries only deepen. Why do giraffes sleep so little without failing? How do migrating birds recover memory after weeks of microrest? What happens in the minds of octopuses when their skin flashes patterns in dreams? Science continues to search for answers, but one truth stands firm. Sleep, in whatever form it takes, is not weakness or waste. It is the quiet engine of survival, humming beneath every heartbeat in the living world. When we look across this vast variety, one message becomes clear. Rest is life's oldest strategy for balance. Whether curled in a den, drifting in currents, or gliding beneath stars, creatures pause in their own ways to restore. It is a reminder that sleep, far from being uniform, is as diverse as life itself. When we think of rest, we often imagine cozy burrows, nests, or sheltered corners. Yet many creatures face the challenge of sleeping in the open, where predators or harsh elements are constant threats. Their solutions are some of the most remarkable adaptations in the natural world. Take marine birds nesting on cliffs. Guillemots and murres perch on narrow ledges, with chicks huddled against sheer drops. Here, sleep is shallow and brief, as constant awareness prevents falls. Studies show these birds close one eye at a time, a form of unihemispheric sleep like dolphins, keeping half the brain vigilant. Their survival depends on balancing restoration with alertness in dangerous perches. On open plains, prey animals such as antelope, zebras, and wildebeests often rest in groups. Rather than hiding, they rely on numbers. Individuals take turns keeping watch while others sleep. Eyes remain half open, ears twitch constantly, and naps are short. If danger approaches, the group reacts as one. For such species, rest is a social act, distributed among members. Seals face a similar issue at sea. Floating at the surface, they risk drifting away or attracting predators. Some species adopt a posture called bottling, with their noses pointing upward like floating corks. This keeps airways above water while bodies remain still. These naps may last only minutes before the seal stirs, swims, and resettles. On land, where threats are fewer, they enjoy longer bouts. The ability to switch patterns depending on location shows rest's flexibility. Then there are animals that literally sleep while moving. Horses can rest standing thanks to a stay apparatus, a system of ligaments and tendons that lock joints, preventing collapse. This lets them nap without lying down, ready to flee at the first sign of danger. They still need to lie down occasionally for REM, but the majority of rest comes standing. Camels use similar systems, important for survival in deserts where lying flat could expose them to scorching sand or predators. Sharks bring an even stranger case. Some species, like the great white and mako, must keep water flowing over their gills to breathe. For them, stopping entirely is impossible. Instead, they enter slow, reduced activity states while continuing to swim. Others, like nurse sharks, can rest on the seafloor, pumping water actively. In all cases, survival dictates how much stillness is allowed. Flying animals show equal ingenuity. Swifts are thought to spend months aloft, rarely landing. Evidence suggests they nap in gliding flight, wings outstretched, carried by thermals. These naps may last seconds, adding up over days. Similarly, frigate birds can glide for hours, snatching brief episodes of half-brain rest while soaring high. For them, sleep is fragmented into countless pieces, woven seamlessly into continuous motion. One of the strangest strategies belongs to dolphins with newborn calves. For weeks after birth, neither mother nor calf fully rests. Instead, they remain in near-constant motion, swimming slowly day and night. Scientists believe this protects calves from predators and ensures they surface for frequent breaths. Only after several weeks do mother and calf return to more typical half-brain rest. Incredibly, mothers endure this near sleeplessness without obvious harm, suggesting extraordinary adaptations for such demanding periods. Insects, too, face their own challenges. Bees, for example, often rest in exposed positions. At night, workers may cling to flowers, antennae drooping and bodies still. Solitary bees sometimes cluster together, forming living chains as they sleep. Though vulnerable, this behavior likely reduces predation risk by confusing or overwhelming attackers. Butterflies roost in similar ways, wings folded tightly, entering a motionless state until sunlight warms them again. Bats invert this idea entirely. They roost upside down in caves or trees, using specialized tendons that lock claws closed without effort. This lets them hang safely for hours, even in deep sleep. Colonies of thousands may cluster together, body heat and darkness providing protection. For them, the greatest danger is disturbance. If startled awake, bats launch into chaotic swarms, filling skies in an instant. Their sleep depends on safety in numbers and concealment. Among reptiles, crocodiles present a curious example. Studies with cameras and brain sensors revealed that crocodiles can keep one eye open during rest, watching surroundings, while half the brain remains alert. This resembles unihemispheric sleep in birds and dolphins, hinting at independent evolution of the same adaptation. Even these ancient predators must balance restoration with awareness. The strategies reveal a clear truth. Sleep is shaped less by internal needs alone and more by the demands of environment. Whether clinging to cliffs, floating in seas, standing on plains, or soaring in skies, animals rest in ways that minimize risk. Vulnerability has sculpted rest into countless ingenious forms, but not all oddities come from danger. Some animals seem to need remarkably little sleep, raising questions about why they differ. Elephants and giraffes, for example, rest only a few hours each day, yet they thrive. How do they function without the long stretches we consider necessary? Part of the answer may be efficiency. Their brief sleep may be richer in slow wave or REM phases, condensing benefits into shorter periods. Another factor is energy demands. Constant foraging leaves little time to spare. Evolution may have favored minimal rest as the best compromise. Other animals are the opposite, spending most of life asleep. Sloths, for instance, famously nap up to 15 hours a day. Yet early studies overestimated this by using captive animals, where boredom and safety inflated resting times. In the wild, sloths sleep closer to 9 or 10 hours, still long but not extreme. Their slow metabolism, leafy diet, and tree-dwelling lifestyle make extended rest practical. Koalas show an even stronger example. They consume eucalyptus leaves, low in nutrients and full of toxins. Processing such a diet demands long digestion and low energy use. As a result, koalas sleep up to 20 hours daily, conserving strength while their stomachs work. For them, slumber is survival, the only way to cope with such limited food. Contrast this with predators like lions. After a big hunt, lions may sleep 20 hours, conserving energy for the next chase. As apex hunters, they can afford such indulgence, safe from most threats. Yet when food is scarce, they may remain alert for days. Their sleep is feast or famine, shifting with circumstance. Domestic cats show a diluted version, often dozing 16 hours a day. Unlike wild relatives, they live in safety, with food provided. Their sleep expands to fill the available time. Anyone with a cat has seen this, curled in sunbeams, twitching in dream hunts. The variety across species underscores the flexibility of sleep. It is not measured by hours alone, but by context. An elephant thrives on 2, a koala requires 20, and both are equally adapted. Sleep also carries cultural significance among social animals. Primates often share nests or sleeping trees, with group safety allowing deeper rest. Young are cradled by mothers or surrounded by kin. This social rest strengthens bonds while reducing danger. In some monkeys, dominant individuals take central safe spots, while subordinates sleep on edges. Social rank even influences rest. Humans reflect similar patterns. In ancient times, people likely slept in groups, with some awake while others rested, a rolling watch not unlike ducks at the edge of flocks. Modern solitary bedrooms are an unusual invention. Evolutionary echoes remain in our tendency to wake easily in new places or stir at faint noises. The vulnerability of rest has shaped us, too. Looking deeper, we find not only practical adaptations but mysteries. How do elephants maintain memory with so little REM? Do whales dream when half their brain rests? What images fill the minds of octopuses flashing colors in active sleep? These questions remain unanswered, yet each clue points to one truth: sleep, no matter how strange, is essential. The science of rest continues to grow. New technologies allow us to track wild animals with tiny sensors, revealing patterns never imagined. What once seemed simple, closing eyes and lying still, emerges as a kaleidoscope of adaptations. Sleep is not a single state but a spectrum, tuned to the needs of every species. From cliffs to deserts, from coral reefs to jungle canopies, animals pause in ways that balance restoration and survival. Their strategies, whether half-brain vigilance, group rotations, or upside-down roosts, remind us of the creativity of life. Sleep is universal but never uniform. In its infinite shapes, it reveals the ingenuity of survival itself. Rest is not only about safety or survival, it also shapes memory, learning, and even creativity. Across the animal kingdom, researchers have uncovered fascinating connections between sleep and intelligence. The way creatures rest may determine how they remember, solve problems, or even communicate. In mammals, strong evidence links sleep with memory consolidation. Experiments with rats running mazes revealed that patterns of brain activity recorded during exploration repeat while they sleep. It is as if the brain replays the journey, strengthening the neural pathways. Deprive the rats of rest, and they forget routes or learn them far more slowly. This shows that sleep is not wasted time but active mental rehearsal. Birds offer equally striking examples. Songbirds, such as zebra finches, spend their early lives practicing songs. During rest, their brains replay the neural patterns of singing, even when silent. Juveniles deprived of sleep struggle to learn proper songs. Adults use rest to refine and stabilize tunes, ensuring complex communication. In this way, sleep becomes rehearsal for cultural transmission. Without it, songs collapse. Humans share this trait. Students deprived of sleep recall far less. Athletes perform worse when under-rested. Musicians and artists often credit dreams with creative insights. Famous cases, like chemist Kekulé dreaming of a snake biting its tail, show how sleep can provide breakthroughs. The brain, freed from outside distractions, may forge new connections. Even insects reveal this link. Fruit flies deprived of sleep show impaired learning. Bees that miss rest fail at navigation, unable to remember routes back to hives. The pattern is clear. Across species, sleep is vital for learning and memory. The role of dreams in this process is still debated. Some scientists argue that REM, where dreams occur, is essential for processing emotions and memories. Others believe slow-wave non-REM is equally important, offering a chance for the brain to replay and strengthen knowledge. Perhaps both are true, different stages supporting different types of learning. Consider octopuses again. Their vivid REM-like phases may not only reflect memories but also problem-solving. In captivity, octopuses have been seen opening jars, escaping enclosures, or manipulating objects. Could dreams serve as practice? We cannot know for sure, but the possibility suggests that intelligence itself may depend on rest. This link raises fascinating questions about evolution. Did the need for memory and learning drive the complexity of sleep? Did creatures with richer REM gain advantages in adapting, surviving, and passing knowledge? If so, dreaming may not be a strange byproduct but a cornerstone of intelligence. Yet rest does not always serve the mind alone. Physical repair is equally vital. During deep non-REM, growth hormones peak, helping tissues recover from strain. The immune system strengthens, producing proteins that fight infection. Muscles relax, blood pressure lowers, and cells repair. Sleep-deprived animals become sick more easily, wounds heal slowly, and survival rates drop. The immune connection is profound. In experiments, mice deprived of rest died faster from infection. Humans missing sleep are more likely to catch colds after exposure. Vaccinations are less effective if recipients are sleep-deprived. This suggests that across life, rest is woven tightly into defense systems. The brain itself is also cleaned during sleep. The glymphatic system, discovered only recently, clears out waste like beta amyloid, a protein linked to Alzheimer's. This system is most active during deep non-REM. Without rest, toxins accumulate, possibly contributing to disease. In this sense, sleep is like nightly housekeeping, flushing harmful buildup. This may explain why even animals with minimal sleep, like elephants, cannot abandon it entirely. A few hours of slow wave may be enough to trigger these crucial processes. Whether 2 hours or 20, the quality of sleep matters as much as duration. The diversity of patterns also reveals how animals balance competing needs. Predators like lions can indulge in long rest, safe in their dominance. Prey must limit vulnerability. Migrators squeeze sleep into flights. Each solution reflects the pressures of lifestyle, but sometimes those pressures push rest into extremes. Take desert rodents, which burrow underground to escape heat. They sleep during the day, surfacing at night. Polar animals face opposite extremes, endless daylight or darkness. Caribou adjust by resting in scattered naps, not following strict day-night cycles. Penguins in bright polar summers sleep hundreds of times a day, each nap a few minutes. Their brains accumulate rest in fragments. In caves, rhythms vanish entirely. Blind cave fish show no circadian patterns, drifting between active and inactive states at random. Rest is untied from day and night, shaped instead by food or currents. This flexibility demonstrates that while circadian rhythms guide sleep, they are not the only drivers. Survival rewrites the rules. Some of the most striking variations appear in captivity versus the wild. Animals in zoos often sleep longer, freed from threats and foraging. Lions in captivity may rest up to 20 hours daily, more than their wild kin. Sloths, once thought to sleep 20 hours, were found in the wild to sleep closer to 10. Safety, diet, and stimulation all reshape rest. This highlights that natural sleep is not always mirrored in artificial settings. The role of environment is further seen in experiments with constant light or dark. Hamsters exposed to unchanging conditions show drifting cycles, proving that light is a crucial anchor. Without it, internal clocks run slightly long or short. Humans, too, demonstrate this. In underground experiments, people without clocks or sunlight often develop 25-hour cycles, drifting gradually later each day. Sunlight resets us daily, preventing this slide. Even so, not all creatures depend on light. Some use tides, aligning activity with lunar cycles. Crabs and other marine animals follow rhythms of high and low tide, their rest woven into ocean movements. Others use temperature, synchronizing with daily warmth and coolness. Evolution has provided countless timekeepers. This diversity underlines a key point. Sleep is not uniform but endlessly adaptable. Its functions remain constant: repair, memory, defense. But the form shifts to fit environment, size, diet, and lifestyle. From bees drooping on flowers to whales drifting in deep seas, each species writes its own pattern on this ancient rhythm. And yet the mysteries persist. Why do some thrive on almost no REM? Why do others need so much? How do tiny bursts of sleep restore migrating birds? Do cephalopods truly dream in color? These questions remind us how much remains unknown. Sleep is universal, yet still one of biology's deepest enigmas. As science advances, the answers may illuminate not only the lives of animals but our own. For if sleep shapes memory, creativity, health, and survival across all species, then its role in humanity may be even greater than we realize. We are not separate from this rhythm but part of it, bound by the same nightly currents that guide dolphins, birds, and bees. The story of sleep is not about stillness. It is about activity hidden beneath calm, cycles of repair, memory, and imagination. Every creature, from insect to whale, rides these cycles in its own way. Together they form a universal truth. Life cannot thrive without surrendering to the quiet power of rest. When we look closely at the animal kingdom, it becomes clear that sleep is not a luxury. It is a necessity, though expressed in endlessly creative ways. Yet what happens when animals are deprived of it? The answer reveals just how vital rest is to survival. In controlled studies, rats forced to remain awake eventually died within weeks. Before death, they showed dramatic symptoms: loss of weight despite increased eating, inability to regulate body temperature, sores on their skin, and eventually systemic failure. Sleep deprivation proved as lethal as starvation. This highlights that rest is not simply recovery, it is as essential as food and water. Birds show similar costs. Pigeons deprived of rest lose balance, stop grooming, and eventually weaken. Songbirds stripped of REM phases lose the ability to sing properly. Their tunes become sloppy, failing to attract mates or defend territories. In the wild, such impairment could mean the difference between survival and extinction. Even insects pay the price. Sleep-deprived fruit flies become less coordinated, less fertile, and die earlier. Bees without rest cannot remember flower patterns or navigate back to hives, undermining the survival of entire colonies. For creatures large and small, rest is the backbone of daily life. Humans too show rapid decline without sleep. After a single night of deprivation, focus and memory falter, reaction times slow, emotional balance wavers, leading to irritability and anxiety. After days, hallucinations appear, and the body struggles to regulate temperature and immunity. While we rarely reach extremes, even mild deprivation carries heavy costs. The universality of these effects suggests that sleep performs ancient, irreplaceable functions. Whether cleaning the brain, consolidating memory, or repairing tissues, it cannot be bypassed without consequence. The exact reasons may differ among species, but the necessity remains absolute. Interestingly, some animals can endure partial deprivation without collapse, using recovery strategies. Migrating birds, for instance, reduce sleep during long flights, then repay the debt upon landing. Marine mammals with newborn calves may remain nearly sleepless for weeks, but later return to normal patterns. This suggests that while deprivation is dangerous, flexibility exists. Sleep debt can be postponed temporarily but never erased. The phenomenon of rebound sleep is key. When deprived, animals often enter deeper, longer phases once allowed to rest. Rats denied REM later spend more time in REM. Humans deprived of deep non-REM slip into it more quickly the next night. This shows the brain actively compensates, prioritizing what was missed. Sleep is not optional, it is managed with urgency. The study of deprivation also reveals the dangers of modern environments. Artificial light, noise, and constant stimulation affect human rhythms. Shift workers exposed to irregular schedules face higher risks of illness. Jet lag, though temporary, shows how sensitive circadian systems are to disruption. These same pressures affect animals in cities, where lights, noise, and human presence alter rest. Birds in urban areas sing earlier and sleep less. Bats avoid noisy regions. Even fish near constant light sources lose natural rhythms. In this way, our influence reaches deeply into the rest cycles of other species. The more we study, the clearer it becomes. Sleep is not just for recovery but for resilience. It sustains life at every level: physical, mental, and social. Hibernation adds another fascinating layer. Though not identical to sleep, it shows how rest can be stretched across time. Ground squirrels enter torpor for months, body temperature dropping near freezing, heart slowing to a few beats per minute. Yet even in these states, they must wake briefly every few weeks to enter normal sleep. This proves that hibernation cannot replace the functions of true sleep. Something essential happens only in regular non-REM and REM. Bears, in contrast, do not cool as much but remain inactive for months, drawing on fat reserves. Their bodies recycle waste products, preventing muscle and bone loss. While they rest deeply, they still rouse occasionally. Mothers even give birth during this period, nursing cubs in a drowsy half-wakefulness. Their form of dormancy lies between true hibernation and sleep, a spectrum showing nature's adaptability. Torpor also appears in smaller creatures on shorter timescales. Hummingbirds, for example, enter nightly torpor when food is scarce, dropping metabolism to survive cool nights. Some bats do the same, conserving energy during lean times. These short-term shutdowns illustrate how flexible the line between rest and torpor can be. Migration pushes adaptations even further. Bar-tailed godwits fly thousands of miles without stopping. To achieve this, they suppress sleep almost entirely. On arrival, they collapse into long recovery bouts, making up the deficit. White-crowned sparrows show similar patterns during migration. In captivity, they can endure prolonged wakefulness with fewer deficits than expected, suggesting special adaptations. What unites all these cases is resilience. Sleep can be delayed, fragmented, or altered, but never removed. Every creature must eventually surrender, even if only in short bursts. This resilience reveals an evolutionary truth. The benefits of rest are so critical that survival strategies bend around them. Consider also the curious phenomenon of microsleep. When deprived, animals and humans alike slip into brief unconscious moments, often lasting only seconds. Eyes may remain open, but awareness fades. Drivers fall into microsleeps behind the wheel, with deadly consequences. Rats show them when kept awake too long. These involuntary lapses demonstrate the body's insistence. If rest is denied, it will force its way in. This insistence also highlights another question: what counts as true sleep? Some animals blur the line. Jellyfish without brains pulse less at night and respond more slowly. If disturbed repeatedly, they show rebound the next day, a hallmark of real sleep. Fruit flies with tiny nervous systems also demonstrate clear rest patterns. Even single-celled organisms show daily rhythms, though not true sleep. These discoveries suggest that the roots of rest may lie deep in the tree of life, perhaps predating complex brains. Dreaming remains one of the most captivating aspects of deprivation research. In humans, REM loss leads to intense rebound, with longer, more vivid dreams once allowed. Similar rebound appears in cats and rats. This suggests dreams serve vital roles, perhaps in processing memory or regulating emotion. Denied too long, the brain demands them back. The persistence of dreaming across species suggests ancient importance. Why would evolution conserve such activity unless it offered strong benefits? Whether rehearsing tasks, strengthening memory, or balancing emotions, dreams seem more than idle imagination. They are necessities of the mind. The consequences of deprivation extend to society as well. In colonies of ants or bees, sleepless individuals disrupt group function. Bees that miss rest navigate poorly, harming foraging efficiency. Ants deprived of sleep grow less effective at cooperative tasks. Social insects show that rest is not only personal but communal, affecting entire colonies. Similarly, in primates, lack of rest disrupts social bonds. Grooming, play, and cooperation decline. The effects ripple outward. For humans, the parallels are obvious. Sleep-deprived societies face higher risks of accidents, lower productivity, and poorer health. Our own rest is deeply entwined with community well-being. In this, we are not separate from animals but aligned with them. Looking at the big picture, sleep deprivation underscores sleep's essential nature. It strips away illusions of luxury or weakness, revealing rest as a biological necessity. From rats in labs to birds in skies, from bees in fields to humans in cities, the story is the same. Deprive sleep and systems fail. Allow it and life thrives. Perhaps this explains why, despite its risks, rest never disappeared from evolution. Even the most vulnerable prey animals, sleeping lightly and briefly, still surrender to it. Even creatures in constant motion, birds in flight, dolphins in seas, still find ways to rest. Evolution could not erase it because survival without it proved impossible. In the end, sleep is the great equalizer. Predator and prey, giant and insect, bird and whale, all must bow to its power. It is the thread connecting every heartbeat, every memory, every dream. Without it, life unravels. With it, life endures. Among the many mysteries of animal sleep, few are as captivating as the presence of dreams. Humans spend about a quarter of their rest in REM, the stage most strongly tied to dreaming. But as we saw earlier, REM or REM-like states occur in a wide range of species. This raises the question, what do animals dream about and why? Dogs and cats provide some of the most familiar hints. Anyone who has shared a home with them has seen paws twitching, whiskers flicking, or muffled barks and meows during rest. These movements strongly resemble behaviors from their waking hours. A dog may be chasing a ball in its dreams, a cat hunting birds in imagined fields. The parallel is so striking that scientists believe their dreams replay daily experiences, much like ours. Rodents offer clearer scientific evidence. In experiments, rats trained to run mazes showed brain activity while asleep that mirrored the same neural firing patterns recorded during exploration. This suggests they were replaying the maze in dreams, consolidating memory. When deprived of REM, their performance the next day dropped significantly. For them, dreaming was rehearsal, practice carried out within the mind. Birds add another layer. Songbirds, especially zebra finches, display brain activity during sleep that matches singing. Young birds learning songs replay practice sessions silently in dreams. Adults refine tunes overnight, stabilizing melodies. Deprived of sleep, they falter, their songs becoming sloppy. Here, dreaming appears directly tied to communication and mating success. Reptiles once seemed outside this pattern, thought to lack REM altogether. But recent studies on Australian lizards revealed alternating states resembling REM and non-REM. The REM-like phases showed eye movements and neural activity, suggesting possible dream states. This discovery pushes the origins of dreaming back hundreds of millions of years, suggesting it may be far more ancient than once assumed. Cephalopods show the most dramatic displays. Octopuses and cuttlefish enter active sleep phases where their skin flashes patterns and colors in rapid sequence. One moment pale, the next striped or mottled. Combined with body twitches, these episodes look remarkably like dream enactments. Some scientists speculate they may be reliving hunts, escapes, or social encounters. The complexity of their behavior and nervous systems supports the idea that cephalopods experience vivid inner worlds. Why dream at all? Several theories compete. One is rehearsal. Dreams allow practice for survival tasks, from hunting to evasion. Another is memory. Dreams consolidate and organize experiences, strengthening useful memories while discarding noise. A third is emotional regulation. By replaying stressful or strange events in a safe setting, dreams help creatures adapt emotionally. For humans, evidence supports all three roles. Athletes dreaming of skills improve faster. Traumatic memories soften over time through dreaming. Creative solutions often appear after sleep. These benefits likely apply across species, each shaped to its own needs. The persistence of dreaming in evolution suggests it provides survival advantages. If REM were useless, it would have disappeared long ago. Instead, it remains widespread, appearing in mammals, birds, reptiles, and cephalopods. This indicates deep evolutionary roots, stretching back perhaps to the earliest nervous systems. The content of animal dreams remains unknowable, yet glimpses suggest common themes. Dogs may relive chases, cats hunts, birds songs, rats mazes, octopuses shifting seascapes. These are not random images but reflections of waking life. Just as human dreams mix memories, fears, and hopes, animal dreams likely weave daily experiences into strange tapestries. Dreaming also reveals the paradox of sleep. It seems like vulnerability, lying still, eyes closed, unresponsive. Yet within, the mind is alive, weaving simulations that prepare the animal for life. Sleep is not absence but hidden action, and dreams are its secret work. Beyond dreams, another striking feature of rest is its relationship with social life. Many animals sleep not alone but in groups, and their strategies reveal much about cooperation. Meerkats, for instance, sleep in communal burrows. Pups nestle in the center, adults around the edges. Some individuals take sentinel duty, awake at entrances while others rest. This rolling watch ensures safety without leaving anyone vulnerable for long. Baboons and other primates often rest in trees, groups huddled on branches. Position matters. Dominant individuals claim safer, central spots, while subordinates rest on the edges. This reflects social hierarchies even in slumber. Yet the group benefits overall, as collective safety allows longer and deeper rest than solitary life could provide. Birds show similar group strategies. Flocks roost together on branches or cliffs. As noted earlier, ducks on the edges keep one eye open, while those in the center sleep more deeply. Rotating positions spreads risk. Colonies of starlings or swallows may contain thousands of individuals, their synchronized settling a breathtaking display. Group rest here balances individual vulnerability with collective strength. Bats take the idea further. Roosting in caves, tens of thousands may cluster in dark colonies. Their safety comes from numbers and concealment. Disturbance sends waves of bats swirling into the night, a defense through confusion. For them, sleep is social both for warmth and security. Even marine mammals show group strategies. Dolphins often rest in pods, individuals taking turns closing one eye while swimming slowly together. The group provides safety from predators, while unihemispheric rest allows constant motion. Mothers with calves benefit especially, supported by the group during sleepless early weeks. Social sleep highlights that rest is not only biological but cultural. It shapes and reflects group structures, hierarchies, and cooperation. The simple act of where one sleeps reveals much about relationships. Humans are no exception. Archaeological and anthropological evidence suggests that for most of history, people slept in groups, families or tribes huddled near fires or in shelters. Watch shifts were likely common, ensuring someone stayed alert. Our modern practice of solitary bedrooms is unusual. Even today, many cultures favor communal rest. Evolutionarily, humans too were shaped by social sleep. Our sensitivity to noise in unfamiliar places may be a remnant of this history, a partial night watch. The universality of social rest suggests it provides advantages beyond safety. It fosters bonding, grooming before sleep, huddling for warmth, synchronized rhythms, all strengthen group ties. Rest is not merely absence of activity but part of social life, woven into cooperation and trust. From dreaming dogs to huddling baboons, rest reveals hidden sides of life. It shapes memory, learning, creativity, safety, and society. What once seemed like simple stillness emerges as a complex dance of biology and culture. And yet mysteries remain. How do cephalopods experience dreams without our form of consciousness? How did REM evolve independently in reptiles and mammals? Why do some animals rely so heavily on dreams while others seem to need little? Science continues to explore these questions, but one truth shines. Rest is not passive. It is active life playing out within. The story of animal sleep teaches us humility. We see our dreams as unique, our patterns as complex. Yet across Earth, countless creatures drift into strange inner worlds, replaying lives, solving problems, or simply recovering. Sleep connects us, a universal bond uniting mammals, birds, reptiles, insects, and even brainless jellyfish. Every night when eyes close and the world fades, we join this ancient rhythm. Around us in forests, oceans, caves, and skies, billions of other beings surrender too. Each follows its own pattern, yet all share the same truth. Without sleep, there is no life. With it, there is memory, growth, creativity, and connection. In the quiet of night, under the slow turning of stars, the living world breathes together in rest. Dreams ripple through brains and nerve nets, bodies heal, societies strengthen. It is not silence but the soft hum of survival, pulsing through every sleeping creature on Earth. Sleep may be universal, but it does not always look like closing eyes in quiet darkness. Some animals enter strange halfway states, neither fully awake nor fully asleep. These unusual forms of rest challenge the idea that sleep is simple or uniform. One such state is torpor. Unlike deep hibernation, torpor can occur daily, lasting hours instead of months. Hummingbirds provide a striking example. Their rapid metabolism demands near-constant feeding, and at night, when nectar is unavailable, they risk starvation. To survive, they drop body temperature dramatically, slow their heart rate, and reduce metabolism. In this state of torpor, they resemble tiny frozen statues clinging to branches. At dawn, they warm themselves, often shivering intensely before bursting into flight. Without torpor, hummingbirds would not endure cool nights. Bats also rely on torpor, especially in temperate regions. Many species drop into this state when insects are scarce. Some alternate between normal sleep and torpor depending on conditions. This flexibility allows them to survive unpredictable food supplies. Mice, shrews, and other small mammals also use torpor, balancing energy demands with recovery. The boundary between torpor and true sleep is blurry. During torpor, animals show reduced responsiveness, but they also cycle through brain states resembling sleep. The fact that even hibernators wake occasionally to enter normal non-REM and REM suggests that torpor does not fully replace sleep's functions. Instead, it serves as a survival extension, conserving energy during scarcity. Another unusual form is estivation, the warm weather equivalent of hibernation. Amphibians such as lungfish burrow into mud during droughts, sealing themselves in mucus cocoons. There they remain, motionless for months until rains return. Snails and reptiles also estivate, slowing metabolism through dry seasons. While not identical to sleep, estivation shows how rest and energy conservation merge in diverse environments. Even stranger are cases of animals that seem to suppress sleep almost entirely during certain life stages. Male sandpipers, for instance, may remain nearly sleepless during mating seasons, competing continuously for mates. Despite minimal rest, they remain alert and capable, only repaying debt afterward. Migratory birds, as discussed earlier, can cross oceans with barely any rest, delaying repayment until safe arrival. Dolphins with newborn calves swim for weeks without typical rest, mothers and calves remaining constantly active. These cases reveal that sleep, while essential, can bend dramatically to meet survival pressures. The phenomenon of partial rest also appears in humans, though less dramatically. In unfamiliar places, people often sleep lightly, with one hemisphere of the brain more alert than the other. This first night effect may be an evolutionary remnant of unihemispheric sleep, keeping us cautious in new environments. We do not match dolphins or ducks, but traces of the same adaptation remain. Extreme environments provide further insight. In the Arctic, animals face months of constant light or darkness. Circadian rhythms tied to day-night cycles must adapt. Reindeer and caribou, for example, lose clear daily rhythms during these times, resting in scattered bouts instead. Penguins breeding in polar summers nap hundreds of times daily, each nap lasting only minutes. In deserts, nocturnal animals like jerboas and fennec foxes rest through the heat of day, emerging at night to forage. Each adaptation reflects not just biology but survival in demanding worlds. Caves present a different challenge: perpetual darkness. Cave fish, blind and living without sunlight, show disrupted circadian rhythms. Instead of clear patterns, they drift in cycles shaped by food or currents. Bats in caves also alter rhythms depending on season, hibernating in winter and becoming active in summer. Without environmental cues, sleep becomes flexible, guided by necessity rather than light. Marine life also faces unique pressures. In the deep sea, where light never penetrates, rhythms are often tied to food drifting from above or to tidal currents. Some deep-sea creatures show nearly constant low activity, alternating between shallow rest and bursts of motion. Others maintain rhythms tied to surface cycles, even though they never see sunlight. This suggests biological clocks can persist even without external cues, inherited from ancestors closer to the surface. These adaptations demonstrate how profoundly environment sculpts rest. Sleep may be essential, but its form bends around conditions. Whether through torpor, estivation, suppression, or altered rhythms, creatures shape rest to fit survival. Another unusual aspect of rest lies in its relationship with danger. For prey species, vulnerability during sleep drives remarkable strategies. Deer, for example, often rest in open areas where sightlines are clear. Instead of hiding, they rely on spotting predators early. Their rest is shallow, ears flicking, eyes often half open. Rabbits, too, nap lightly, ready to bolt at the faintest disturbance. Predation risk shapes not just where they sleep but how deeply they can enter rest. Predators, by contrast, often indulge in longer, deeper rest. Lions may sleep 20 hours after a large meal, secure in their dominance. Bears hibernate for months, largely free from fear. Wolves, while more active, still rest deeply in dens when safe. Yet even predators are not immune. Cubs or pups remain vulnerable, requiring protection from adults. Safety always determines the quality of rest. Some animals take unique approaches to danger. Armadillos dig burrows, resting underground with armored shells as protection. Hedgehogs curl into spiny balls, sleeping through threats. Turtles retreat into shells, motionless for hours. These behaviors extend physical defenses into the realm of rest, allowing deeper sleep in dangerous settings. The balance between vulnerability and restoration may explain the diversity of sleep durations. Short sleepers like giraffes and elephants may be sacrificing rest for vigilance. Long sleepers like bats and koalas may afford safety through concealment or unpalatable diets. Each strategy reflects the eternal trade-off between safety and recovery. Beyond safety, rest also influences reproduction. In some species, mating displays and songs are strengthened by sleep. Songbirds deprived of rest sing poorly, reducing chances of attracting mates. Male sandpipers that endure sleeplessness during mating seasons succeed only if they can maintain stamina, proof that even sleep suppression carries costs and requires extraordinary resilience. For mothers, rest plays vital roles during pregnancy and care. Many animals reduce activity during gestation, conserving energy. After birth, mothers face sleepless periods while nursing or protecting young, often supported by group structures. Rest here becomes a social, as well as biological task. The intersection of sleep, reproduction, and survival illustrates how deeply intertwined rest is with life cycles. It is not separate from feeding, mating, or migration, but woven into each, adapting as needed. Even parasites and symbiotic organisms play roles in sleep. Birds with lice or mites sleep less, disturbed by itching. Infected animals may rest more or less depending on disease. Sleep interacts with health in complex ways, sometimes helping recovery, other times disrupted by illness. Humans mirror this. Sickness often brings more rest, a natural response aiding healing. From the smallest insects to the largest whales, these patterns reveal that rest is not uniform but infinitely adjustable. Sleep bends to season, danger, food, reproduction, and illness. It is one of life's most flexible tools, yet never optional. As scientists continue to study, the puzzle only deepens. Why can elephants thrive on 2 hours while koalas need 20? How do birds survive ocean crossings with only seconds of rest? What do octopuses see when their skin flashes colors in REM-like states? Each discovery answers one question and opens 10 more. But through all this variety, one truth remains. Sleep is universal. Whether in caves or deserts, forests or seas, under endless daylight or constant dark, every creature must find its way to rest. The forms differ wildly, but the necessity never changes. Sleep, in all its strangeness, is a reminder of life's resilience. Creatures bend it, shape it, and reinvent it, but never escape it. Beneath every adaptation lies the same quiet truth. Survival requires surrendering to stillness, even if only for seconds at a time. The more we learn about animal sleep, the clearer it becomes that it is not only about biology, but also about behavior and culture. In social species, how and when individuals rest reflects cooperation, hierarchy, and survival strategies shared across groups. Consider primates. Many monkeys and apes construct nests or platforms each night. Chimpanzees carefully weave branches into sturdy beds, sometimes even adding leaves for comfort. These nests are not random but deliberate, providing safety from predators, support for bodies, and insulation from cold. Studies suggest that building nests improves sleep quality, allowing deeper, longer rest. This may have influenced the evolution of intelligence, as better sleep enhances memory and learning. Gorillas also make nests on the ground or in trees, depending on safety. Youngsters often share with mothers, while older individuals build their own. These nightly routines reflect not only biology but also social learning, skills passed from one generation to the next. Other primates show social sleeping arrangements that mirror their hierarchies. Baboons, for example, roost in trees or on cliffs. Dominant individuals take central, safer spots, while subordinates rest on edges. This distribution reveals rank even during rest. At the same time, the group gains collective protection. Predators face a wall of eyes and ears, even if some individuals drift into lighter sleep. In meerkats, rest is deeply communal. Families curl together in burrows, pups in the center, adults around them. Some take sentry roles, staying partially awake at entrances while others rest. This rolling system ensures safety without depriving individuals of too much sleep. It demonstrates how sleep can be distributed across groups to balance vulnerability. Birds also show elaborate social rest. In colonies of thousands, like starlings or swallows, synchronization is common. Entire flocks settle at once, creating spectacular displays. Ducks on the edges of flocks often keep one eye open, as noted before, while those inside sleep deeply. This division of vigilance spreads risk evenly across the group. Bats push the idea of collective rest to extremes. Colonies may number in the millions, clustered tightly in caves. Heat and safety come from numbers. Disturbance causes chaotic swarms, confusing predators. Here, rest depends on cooperation. Each individual gains security from the presence of others. Marine mammals like dolphins also rest in groups. Pods swim slowly, individuals alternating hemispheric rest while staying coordinated. Calves benefit from this system, sheltered within the group, while mothers balance their sleepless early weeks. Group structures allow safety even in the open sea. These examples show that rest is rarely individual. Even when eyes close, social bonds continue shaping behavior. Rest becomes a shared act, part of cooperation and survival. Humans, too, reflect this history. Anthropologists suggest that for most of our past, people slept in groups, families or bands clustered near fire. Some individuals likely took turns staying awake. Even today, many cultures maintain communal sleeping, with families or communities sharing spaces. Modern solitary bedrooms are unusual in human history. Our tendency to stir at noises in new places, or to sleep lightly on the first night, may be remnants of this evolutionary background. The role of rest in social life extends to reproduction and care. Pregnant animals often rest more, conserving energy. Mothers with newborns may sacrifice their own rest to protect and nurse young, supported by groups when possible. In elephants, females stand watch while calves lie down to sleep. In wolves, entire packs help protect pups, allowing parents some recovery. Sleep here becomes a collective investment in the next generation. Even among insects, social structures influence rest. Bees deprived of sleep lose navigation ability, failing to return to hives. Colonies rely on shared rhythms, with workers alternating activity and rest. Ant colonies show similar patterns, with individuals cycling in shifts so that the group remains active continuously. In such cases, sleep is not only individual restoration, but part of collective function. This communal nature raises intriguing questions about the evolution of sleep. Did group living allow deeper rest by providing safety in numbers? Did the development of nests and shelters improve sleep quality, boosting memory and intelligence? If so, rest may have played a hidden role in shaping the rise of complex societies and even human culture. Beyond social aspects, the diversity of sleep duration still fascinates researchers. Why do some animals need 20 hours while others survive on 2? The answer lies in trade-offs. Bats, for instance, can afford long rest because they are hidden during the day and active only at night. Elephants, needing to travel constantly for food, can only spare a few hours. Koalas sleep nearly all day because their nutrient-poor diet demands conservation of energy. Giraffes, constantly threatened, cannot risk long unconsciousness. Each solution reflects a balance between biology, ecology, and danger. Interestingly, captivity often exaggerates these differences. Animals in zoos may rest far more than wild counterparts, freed from threats and foraging. Lions in captivity may sleep up to 20 hours daily, more than wild lions. Sloths, once thought to sleep 20 hours, were later found in the wild to rest closer to 10. Safety, diet, and stimulation shape patterns as much as biology itself. The study of these differences also illuminates human sleep. Modern humans average around 7 to 8 hours, but this varies across cultures. Some traditional societies sleep less at night but nap during the day. Others rest in multiple short bouts rather than one long block. Polyphasic sleep, common in animals, appears in humans too. It suggests that our current model of consolidated nightly sleep may be cultural more than biological. At the heart of it all lies a paradox. Sleep is universal and essential, yet endlessly flexible. It bends to danger, diet, season, and society. It shapes memory, immunity, reproduction, and culture. But despite this variety, it remains inescapable. Every creature must rest, even if only briefly. The universality suggests ancient origins. Sleep-like states appear even in jellyfish, which lack brains. Their pulsing slows at night, and they show rebound if deprived. Fruit flies, with tiny nervous systems, also exhibit clear rest patterns and rebound. The fact that these simple organisms demonstrate key features of sleep suggests it may predate complex nervous systems entirely. Perhaps rest is as old as movement itself, an ancient rhythm built into the fabric of life. Dreaming adds further depth. Its presence in mammals, birds, reptiles, and cephalopods suggests that inner mental activity during rest is equally ancient. Whether practicing songs, replaying hunts, or flashing colors in imagined seas, dreams seem to serve roles beyond idleness. They may be the training ground of life, rehearsing challenges in safety. From a scientific view, much remains unknown. Why does REM exist? Why does deprivation prove fatal? How do some species condense all benefits into short sleep while others need long stretches? These questions drive ongoing research, with new technologies revealing patterns never seen before. Miniature sensors track brain waves in wild animals, exposing behaviors that captivity concealed. Already, discoveries have overturned assumptions, such as birds sleeping in flight or reptiles experiencing REM-like states. Every new insight expands our view of life's ingenuity. Rest is not absence but adaptation, sculpted by millions of years. It is not weakness but resilience, proof that survival demands cycles of stillness as much as motion. When we close our eyes at night, we join a vast chorus. Lions curl in grasslands, bats cluster in caves, elephants doze briefly under stars, dolphins swim slowly with one eye open. From insects to whales, from deserts to deep seas, every creature surrenders to rest. It is the hidden bond connecting all life, a reminder that survival is not only about action, but about pausing, healing, and dreaming. Sleep, in its countless forms, is life's quiet masterpiece. If sleep is so vital, why does it take such different shapes across the animal world? The answer lies in the delicate balance between needs and risks. Every creature must restore its body and brain, but every moment of stillness invites danger. From this tension, evolution has crafted endless variations. Consider grazing animals on open plains. Giraffes, antelope, and zebras cannot afford long, deep sleep. Their survival depends on vigilance, ready to flee predators at any moment. As a result, they take many short naps, often standing. Giraffes rarely lie flat, and when they do, it is for only minutes. Elephants may travel for days without lying down, sleeping in bursts of just a few minutes at a time. Despite their size and strength, their vulnerability forces extreme caution. By contrast, predators like lions or tigers can indulge in longer rest. With fewer threats and abundant safety in groups, they may sleep for 18 to 20 hours after a successful hunt. This indulgence is not laziness but energy conservation. Chasing prey demands bursts of intense power, followed by long recovery. Lions embody the predator's rhythm, short explosions of activity balanced by long stretches of rest. Koalas provide another extreme. Their diet of eucalyptus leaves is so low in nutrients and full of toxins that they must conserve energy. They sleep up to 20 hours daily, saving strength for digestion. Their bodies are adapted for efficiency, with minimal energy spent on movement. Without such long rest, they could not survive on their meager diet. Sloths are similar. Hanging in trees, they move slowly and rest often. Captive studies once suggested they slept 20 hours, but wild studies revealed closer to 10. Even so, their metabolism is slow, their lifestyle unhurried. For them, rest is not just recovery, but part of an entire strategy of slowness. Small mammals like rodents often sleep much longer than large ones. Mice, hamsters, and shrews may rest half the day. Their high metabolisms burn energy quickly, requiring long recovery. Bats, though predators of insects, rest for 18 to 20 hours daily, partly because they conserve energy during daylight and emerge only at night. Their long sleep is linked as much to lifestyle as to biology. These patterns show that sleep is not measured by intelligence but by ecology. Elephants, with remarkable memory, sleep little. Bats, with small brains, sleep much. The deciding factor is not mental complexity but diet, danger, and environment. Marine mammals highlight this even more clearly. Dolphins and whales, unable to breathe automatically, rest with half their brains. One hemisphere sleeps while the other stays alert, keeping them swimming and surfacing. Their eyes remain half open, scanning surroundings. This unihemispheric sleep is a compromise, preserving life in an unforgiving sea. Seals show flexibility. At sea, they may rest half-brained like dolphins, drifting vertically with noses above water. On land, they lie fully at rest, both hemispheres offline. This dual system allows adaptation to two environments. It demonstrates how sleep is not a fixed design, but a toolkit animals use depending on setting. Birds take this further. Migratory species like swifts or frigate birds can fly for weeks without landing, napping briefly in flight. They enter unihemispheric sleep for seconds, wings locked in glides. When on land, they repay the debt with deeper rest. Ducks in groups show the same pattern, outer ducks keeping one eye open while inner ducks sleep deeply. Sleep rotates through the flock, balancing safety with recovery. Such flexibility shows the central paradox. Sleep is unavoidable yet dangerous. To survive, animals reinvent it constantly. Some fragment it into seconds, some compress it into hours, others stretch it across seasons in hibernation or torpor, but none escape it completely. The consequences of deprivation prove why. Rats forced to remain awake die within weeks. Birds deprived of REM lose songs. Bees without sleep fail at navigation. Humans deprived grow irritable, forgetful, and eventually hallucinate. Sleep may look passive, but its absence reveals its power. Life cannot endure without it. Hibernation and torpor provide fascinating variations. Ground squirrels drop into torpor for months, body temperature near freezing, metabolism slowed to a whisper. Yet even they must wake briefly to enter normal sleep before resuming torpor. This proves that hibernation is not sleep but a complement. True sleep's functions, memory consolidation, immune repair, neural cleansing, cannot be bypassed even in suspended states. Bears show another version. They do not cool as much as rodents but spend months in dens, heartbeat slowed, metabolism reduced. Mothers even give birth during this period, nursing cubs in drowsy half-wakefulness. Their state blends elements of sleep and dormancy, conserving energy through winter. Hummingbirds use nightly torpor, dropping metabolism to survive cold nights when nectar is absent. Their bodies cool dramatically, appearing lifeless until dawn. Without this, they would not survive until morning. Bats do the same, conserving energy when insects are scarce. These short-term shutdowns demonstrate rest's adaptability. Other forms include estivation, used by creatures in hot, dry climates. Lungfish burrow into mud, sealing themselves in cocoons until rains return. Snails withdraw into shells, frogs bury themselves. These states allow survival during harsh seasons, though they, too, eventually return to true sleep cycles. Beyond survival, sleep plays deep roles in learning and memory. Rats rehearse mazes in dreams. Songbirds refine songs. Humans consolidate knowledge. Even insects show learning impairment when deprived of rest. Octopuses in vivid REM-like states may practice hunting or escaping in dreams. Across life, sleep is rehearsal, memory, and adaptation. Dreams remain among the greatest mysteries. Dogs twitch as though chasing prey. Birds replay songs. Lizards enter REM-like states, hinting at ancient origins. Octopuses flash colors, perhaps reliving seascapes. These glimpses suggest that dreaming is widespread, perhaps as old as sleep itself. Why it exists remains debated, practice, memory, or emotion, but its persistence proves its value. Social dimensions deepen the story. Meerkats sleep communally, sentinels guarding while others rest. Chimpanzees weave nests, passing skills across generations. Baboons rest in trees, positions reflecting hierarchy. Dolphins rest in pods, calves sheltered by adults. Bats cluster in millions, gaining safety in numbers. Sleep is not solitary but shared, woven into societies. Humans, too, carry this legacy. For most of history, we likely slept in groups, fires warding predators, some awake as guards. Our tendency to sleep lightly in new places may be an echo of this. Even today, many cultures practice communal rest. Solitary bedrooms are modern inventions, not evolutionary norms. Looking across species, one theme stands out. Sleep is endlessly adaptable but absolutely essential. No creature escapes it. Some surrender deeply, others cautiously. Some dream in colors, others in silence. Some take seconds, others hours. But all must yield. Why? Because sleep is not just stillness. It is repair, memory, creativity, and survival. Without it, bodies break down, minds falter, societies weaken. With it, life flourishes. Every night when we drift into slumber, we join a timeless rhythm shared by every creature on Earth. Elephants standing under stars, lions sprawled in grass, whales floating in oceans, birds gliding in skies, all surrender together. In the quiet across forests, deserts, caves, and seas, the living world breathes in unison. Sleep is not an interruption of life. It is life itself in its most mysterious and essential form. To understand why sleep is so deeply embedded in life, it helps to look at its hidden functions. We often imagine rest as simple recovery, but beneath the surface, it is an intricate biological process that sustains every system of the body. One of the most striking discoveries in recent decades is the brain's cleansing system. During waking hours, neural activity produces waste products, including proteins like beta amyloid. If these accumulate unchecked, they can damage cells and contribute to diseases such as Alzheimer's. During deep non-REM sleep, the brain's glymphatic system becomes highly active. Cerebrospinal fluid flushes through neural tissue, washing away waste. In essence, the brain cleans itself each night. Deprived of sleep, this cleansing falters and harmful buildup remains. This may explain why long-term deprivation is so destructive. Rats forced to stay awake eventually die, not just from exhaustion but from toxic accumulation, immune collapse, and organ failure. Humans deprived of rest suffer memory loss, emotional instability, and impaired judgment, signs of deeper biological strain. Sleep is not optional maintenance, it is nightly survival. Memory consolidation is another crucial function. During sleep, especially REM and deep non-REM, the brain replays and organizes experiences. Important memories are strengthened, trivial ones discarded. Experiments show that students who sleep after studying remember far more than those who remain awake. Rats replay maze runs in dreams, birds rehearse songs, and humans solve problems overnight. Without rest, learning falters across species. Emotional regulation also depends on sleep. During REM, the brain reprocesses experiences, especially those linked to stress. Humans deprived of REM become irritable and anxious. Animals show similar effects, growing restless or less social. By replaying emotions in dreams, the brain softens their impact, helping individuals adapt. This may explain why REM persists across evolution, because it steadies the mind as well as the body. The immune system relies heavily on rest. In deep sleep, the body produces cytokines, proteins that fight infection and inflammation. Mice deprived of sleep die more quickly from illness. Humans lacking rest are more likely to catch colds, and vaccines are less effective when recipients are sleep deprived. Even insects reflect this link. Bees without sleep fail at navigation, harming hive survival. Across the tree of life, immunity and rest are intertwined. The body's growth and repair also occur during sleep. In non-REM, growth hormone peaks, muscles mend, bones strengthen, and tissues rebuild. Athletes sleeping poorly heal more slowly and perform worse. Animals deprived of rest show slower wound recovery. This demonstrates that sleep is not wasted time but active biological work. These functions, cleansing, memory, emotion, immunity, repair, reveal why deprivation is so harmful. They also explain why sleep varies so widely across species. Different animals may prioritize different aspects depending on need. Elephants, with minimal rest, may condense repair into short, efficient bursts. Koalas, with nutrient-poor diets, may require long hours to conserve energy while bodies work internally. Each variation reflects survival demands, but none eliminate the functions entirely. Another key layer is the circadian rhythm. Nearly every organism on Earth has internal clocks aligning activity and rest with environmental cycles. In humans, the suprachiasmatic nucleus above the optic nerve sets this rhythm, responding to light. In animals, rhythms may follow light, tides, temperature, or even social cues. When disrupted, health declines. Humans working night shifts face higher risks of illness. Animals exposed to artificial light lose natural cycles. This highlights how fragile and essential circadian alignment is. Interestingly, not all species rely heavily on circadian rhythms. In polar regions with months of light or darkness, animals adapt by resting in scattered bouts tied to feeding. Caribou and penguins show such flexibility. In caves, blind fish abandon circadian patterns altogether, resting in irregular cycles. This proves that while rhythms are common, they are not absolute. Sleep adapts even when time cues vanish. The study of these rhythms in humans has revealed surprising truths. In experiments where people live without clocks or sunlight, natural cycles often drift longer than 24 hours. Some stretch to 25 or even 26, slowly slipping later each day. Sunlight resets us, preventing this drift. Without it, circadian clocks free run. This shows that our rest depends not only on biology but also on environmental anchors. Light pollution in modern cities disrupts these anchors. Street lights, screens, and artificial glow confuse circadian systems. Birds in cities sing earlier and sleep less. Insects drawn to lights become disoriented, losing natural patterns. Even plants adjust flowering. Sleep is not just a personal rhythm, but part of ecosystems, disrupted by human presence. Technology now allows us to study these patterns in unprecedented detail. Tiny sensors measure brainwaves, heart rates, and movements in wild animals. GPS tags track migrations, revealing sleep in flight. These tools have overturned assumptions, showing frigate birds napping in the sky, reptiles with REM-like states, and whales sleeping vertically. Each discovery expands our view, proving that sleep is far more diverse and creative than once believed. Dream research has also advanced. Brain imaging shows that during REM, areas tied to memory and emotion activate strongly, while rational control quiets. This may explain dream logic, strange, emotional, vivid, yet disconnected. Animals show similar patterns, reinforcing the idea that dreams serve important functions across species. Octopuses provide some of the most compelling evidence. Their REM-like states involve rapid color changes and twitches. Some researchers suggest they may replay memories visually, using skin patterns as external expressions of inner imagery. If true, this would make octopuses not only dreamers but also visible ones, their dreams painted on their skin. The persistence of dreaming across evolution suggests it is not random. Whether for rehearsal, memory, or emotional regulation, dreams provide survival benefits. Without them, animals falter. With them, they thrive. Social sleep adds another dimension. Group rest enhances safety, conserves warmth, and strengthens bonds. Meerkats rotate sentry duty, chimpanzees teach nest building, ducks keep one eye open, bats cluster in millions, dolphins rest in pods. Humans, too, evolved in groups, likely sharing night watches. Sleep is not solitary but social, part of survival strategies across life. The universality of these patterns shows that sleep is not weakness but strength. It is not lost time but essential time, the hidden foundation of life. From cleaning brains to consolidating memories, from regulating emotions to protecting against disease, it is the silent work that sustains every heartbeat. And yet, so much remains unknown. Why do some animals condense all benefits into brief naps, while others require long hours? How did REM evolve independently in reptiles and mammals? What images fill the dreams of octopuses or birds? Each discovery answers one question but opens 10 more. What is clear is that sleep is not optional. It is the invisible engine of survival, powering every creature in ways we are only beginning to understand. Every night across the globe, this hidden work unfolds. Wolves curl in dens, whales float in seas, bees cling to flowers, humans settle into beds. Their forms differ, but their purpose is shared. Sleep in all its diversity binds life together. When we think about sleep, we often picture it as a nightly pause, a simple state of rest. But in truth, it is an active biological process, one that never fully switches off. Even in the deepest stages, the body is busy repairing, regulating, and rebalancing. For animals, the way these processes unfold depends on their environment, size, diet, and evolutionary history. One of the key processes during rest is the regulation of energy. The energy conservation theory suggests that sleep evolved to save resources. During rest, body temperature drops slightly, metabolism slows, and fuel demands decrease. For small mammals with high metabolic rates, long hours of sleep conserve precious calories. For larger animals like elephants or giraffes, short but efficient bouts may be enough. This simple function explains much of the variation across species. Yet energy conservation is not the whole story. Memory and learning also hinge on rest. Rats replay maze runs, songbirds refine tunes, humans consolidate lessons. Bees deprived of sleep lose the ability to remember floral roots. Even fruit flies show impaired learning when rest is withheld. These patterns suggest that one of sleep's oldest functions is strengthening memory. It is as though the brain uses the quiet hours to practice and refine. Repair and growth also unfold during deep non-REM stages. Muscles mend, bones strengthen, immune cells proliferate. The release of growth hormone peaks during rest, guiding development in young animals and healing in adults. Without sufficient sleep, growth falters and wounds heal slowly. This is as true for humans as it is for other mammals. The immune connection is profound. During rest, the body increases production of proteins that fight infection. Sleep-deprived animals succumb more easily to disease. Humans without adequate rest are more likely to catch colds or recover slowly from illness. Vaccines even prove less effective if the body is exhausted. Across species, rest and immunity are deeply linked. The cleansing of the brain may be one of sleep's most essential roles. The glymphatic system, active during deep sleep, flushes waste from neural tissue. Without this nightly cleaning, toxins accumulate. Research suggests this system reduces risk of neurodegenerative diseases. The fact that such a mechanism exists highlights how essential rest is for brain health. But if sleep is so vital, why do patterns vary so widely? Why do koalas need 20 hours, while elephants thrive on 2? The answer lies in ecological trade-offs. Koalas eat nutrient-poor leaves, demanding long hours of conservation. Elephants travel great distances, sacrificing rest for feeding and vigilance. Each species balances the need for restoration against the demands of survival. Even predators differ. Lions may sleep 20 hours when food is abundant but less when hunting is hard. Domestic cats, secure in homes, rest excessively because survival pressures are gone. In the wild, rest contracts and expands with circumstance. Marine life adapts in unique ways. Dolphins and whales rest half their brains at a time, swimming while sleeping. Seals alternate patterns depending on land or sea. Frigate birds nap seconds at a time while soaring over oceans. These strategies prove that sleep is not rigid but fluid, bending to necessity. The flexibility is also seen in seasonal rhythms. Ground squirrels hibernate, yet still wake for short bouts of true sleep. Bears enter dormancy, lowering metabolism but stirring occasionally. Hummingbirds use nightly torpor, appearing lifeless until dawn. In deserts, creatures estivate through heat, conserving energy until rain returns. Each is a unique answer to survival, blending sleep with dormancy. Dreaming adds another layer. Dogs twitch, cats paw, rats rehearse mazes, birds practice songs. Lizards enter REM-like states, octopuses flash colors. These signs suggest that dreaming is ancient, widespread, and purposeful. Theories propose that dreams rehearse survival, consolidate memory, or regulate emotion. Whatever the reason, their persistence across evolution shows importance. Some animals show dramatic suppression of sleep. Male sandpipers stay awake for weeks in mating seasons, competing for females. Migrating birds cross oceans with barely a pause. Dolphin mothers swim with newborns for weeks without typical rest. These cases reveal that sleep can bend almost to breaking, but never fully disappear. Eventually, recovery is necessary. The brain demands its due. Microsleeps reveal this insistence. Humans deprived of rest slip into seconds of unconsciousness, sometimes with eyes open. Rats do the same. Bees falter mid-flight. These brief lapses show that when denied, sleep forces its way in. It cannot be postponed forever. The universality of rest suggests ancient origins. Jellyfish, without brains, pulse less at night and show rebound when deprived. Fruit flies, with tiny nervous systems, display REM-like activity. Even simple organisms show daily rhythms resembling sleep. These findings imply that rest predates complex brains, perhaps arising with the earliest nervous systems. The persistence of circadian rhythms reinforces this. Nearly every organism has internal clocks aligning activity with cycles of day and night. Some follow tides, others temperature. In caves, rhythms drift without cues. In polar regions, animals adapt to endless light or dark. These variations prove that while the form changes, the need remains constant. Social animals show another dimension. Meerkats rest in communal burrows, pups in the center, sentinels on guard. Baboons roost in groups, hierarchies shaping positions. Dolphins swim in pods, calves sheltered. Birds rotate vigilance, outer individuals keeping one eye open. Even bats cluster in millions, gaining warmth and safety in numbers. For such creatures, rest is not just biological but social. Humans reflect this heritage. For most of history, people likely slept in groups, sharing fires and guards. Our modern solitary bedrooms are cultural inventions. The first night effect, sleeping lightly in new places, may be an echo of ancient vigilance. Sleep, even for us, is social as much as personal. Modern life disrupts this. Artificial light alters circadian cues. Noise fragments rest. Shift work, jet lag, and technology interfere with rhythms. Animals in cities adapt similarly. Birds sing earlier, insects circle lights, mammals lose natural patterns. Sleep is delicate, easily disturbed by change. Yet the resilience of rest is equally striking. No matter how disrupted, creatures find ways to recover. Sleep debt is repaid with deeper or longer phases. Functions are prioritized. Even in extreme cases, migrants, hibernators, sleepless mothers, rest eventually returns. This resilience shows its necessity. The more we study, the more mysteries appear. How do elephants thrive with so little REM? What images fill the dreams of cephalopods? How did unihemispheric sleep evolve independently in birds and mammals? Why do some animals compress sleep while others stretch it? Science continues to search, but answers remain elusive. What is certain is that sleep is not weakness. It is not wasted time. It is the foundation of health, memory, emotion, and survival. It binds life across oceans, forests, deserts, and skies. From bees clinging to flowers, to whales floating in seas, to humans drifting into dreams, all are united in this quiet rhythm. Every night the living world surrenders. Eyes close, bodies still, minds turn inward. In caves and burrows, in trees and oceans, in nests and beds, life breathes together in rest. It is a universal language, older than speech, deeper than thought. Sleep is not absence but presence, the presence of healing, memory, and survival. Sleep's diversity shows that it is not a rigid state, but a flexible strategy shaped by countless pressures. Yet even in its most unusual forms, it reveals deep commonalities. Across mammals, birds, reptiles, insects, and even creatures without brains, rest follows familiar rhythms of activity and recovery. To study these rhythms more closely, scientists have turned to technology, and the results have transformed our understanding. Tiny EEG devices now record brainwaves in wild animals. Motion sensors track movements, while GPS reveals migrations. Using these tools, researchers discovered frigate birds napping seconds at a time while soaring over oceans, dolphins resting half their brains as they swim, and reptiles cycling through REM-like states once thought impossible. What once seemed strange exceptions now appear as parts of a larger pattern. Sleep is endlessly adaptable but never absent. One revelation from these studies is just how fragmented sleep can be. Humans often think of rest as one long block at night, but in the animal world, polyphasic sleep, many short bouts, is far more common. Horses nap standing for minutes, then lie down briefly for deeper rest. Seals alternate floating naps with swimming. Penguins in polar colonies take hundreds of tiny naps each day, adding up to several hours. Even humans in traditional societies often sleep in segments, with wakeful periods at night for tending fires, socializing, or reflecting. Our consolidated 8-hour block may be cultural, not natural. Another insight is the role of environment in shaping sleep. Light is a powerful cue, but it is not the only one. Tides guide crabs and other marine animals. Temperature influences reptiles, and food availability drives rest in many species. In deserts, animals sleep through scorching days. In polar regions, they adapt to endless daylight or darkness. Caves strip away cues entirely, leading creatures like blind fish to drift in irregular cycles. Sleep is tied not only to biology, but to the rhythm of the earth itself. Predation risk remains another key influence. Prey animals sleep lightly and briefly, often with one eye open or ears flicking. Predators, by contrast, indulge in longer rest when safe. Yet even predators cannot escape vulnerability. Cubs, pups, or chicks require protection, and social groups often help provide it. Safety shapes not just when animals sleep, but how deeply. Dreaming research has expanded as well. With brain imaging and behavior studies, scientists have found strong evidence that animals dream widely. Rats replay mazes, birds practice songs, dogs twitch in imagined hunts, octopuses flash colors in vivid REM-like phases. The presence of dreams across so many lineages suggests they are ancient, perhaps as old as sleep itself. Theories about dreams remain debated. Some believe they help consolidate memory, others that they regulate emotion, and still others that they rehearse survival tasks. Likely all are true in different measures. What unites them is that dreaming is active mental work, not random noise. Its persistence across evolution argues for value. One striking idea is that better sleep quality may have fueled intelligence. Among primates, nest building improves rest, allowing deeper, longer REM. This in turn enhances memory and learning. Over time, the benefits may have supported the rise of culture and cooperation. Humans, with rich dreams and consolidated rest, may owe part of their intelligence to the quiet hours of night. Sleep, far from being wasted time, could be the very foundation of cognition. Yet mysteries remain. Elephants sleep only a few hours, sometimes skipping entire nights. How do they maintain memory and health with so little? Whales rest half-brained, but do they dream with one hemisphere at a time? How do migrating birds recover after weeks of fragmented rest? Science is only beginning to answer. The universality of sleep suggests deep evolutionary roots. Jellyfish, lacking brains, pulse more slowly at night and show rebound when deprived. Fruit flies with simple nervous systems demonstrate REM-like states. Even these simple creatures reveal the same patterns: reduced activity, rebound after deprivation, and benefits to memory. This implies that sleep is one of life's oldest strategies, predating complex thought. At the same time, human influence now disrupts natural rhythms. Artificial light, noise, and climate change reshape sleep across species. Birds in cities sing earlier and sleep less, drawn by lights. Insects circle lamps endlessly, exhausting themselves. Marine animals near ships are disturbed by constant noise. Even humans suffer from disrupted rhythms, facing higher risks of illness in modern 24-hour societies. Sleep is fragile, easily unsettled by change. Yet resilience persists. Animals adapt, shifting rhythms or redistributing naps. Humans repay debt with rebound sleep. The brain prioritizes what it needs most, whether slow wave for repair or REM for memory. Even in extreme cases, weeks of migration, months of hibernation, sleep's essential functions are eventually reclaimed. These adaptations highlight a profound truth. Sleep is not weakness but strength. It is survival, crafted by evolution into infinite forms. Whether in seconds-long naps, months of dormancy, or vivid dreams painted on octopus skin, sleep sustains life. Looking at the bigger picture, rest reminds us of connection. Every night, billions of creatures surrender together. Bees droop on flowers, lions sprawl in grass, whales float in seas, humans drift into dreams. Their methods differ, but the act is shared. Sleep is a universal bond, a rhythm that unites all living things. This unity challenges us to rethink our own rest. We often see it as lost time, something to minimize. But animals show that it is the opposite, a foundation of survival, learning, and creativity. Without it, life falters. With it, life flourishes. Sleep is not an interruption. It is an essential thread in the fabric of existence, woven through every heartbeat. When we close our eyes, we join a vast chorus of slumbering beings, each following rhythms shaped by millions of years. From deserts to oceans, forests to skies, the living world breathes together in rest. In this stillness lies life's most enduring secret, that to pause is to endure, to dream is to prepare, and to sleep is to live. The story of sleep is the story of life itself. From the tiniest insects to the largest whales, every creature pauses, turns inward, and allows the mysterious process of rest to unfold. But while the need is universal, the methods are astonishingly diverse, shaped by countless pressures: predation, food, climate, migration, and social bonds. Take the example of aquatic mammals again. Dolphins and whales rest with half their brains, a strategy that allows constant swimming and breathing. One eye remains open, watching surroundings, while the other closes. This unihemispheric slow-wave sleep solves problems of vulnerability in oceans full of predators and hazards. Calves complicate the story further, requiring near-constant care. Mothers swim with them for weeks in sleepless states, defying what seems possible. Only later do both return to normal rhythms, showing resilience and flexibility. Birds mirror this with their own unihemispheric rest. Ducks at the edges of flocks keep one eye open, watching for predators, while those inside close both eyes. Migratory birds nap in flight, hemispheres alternating while wings glide on currents. Frigate birds soar for weeks over oceans, sleeping for seconds at a time. When they finally land, they repay their debt with deeper rest. These adaptations prove that sleep bends but never breaks. Reptiles add another piece to the puzzle. Once thought to lack REM entirely, some lizards have shown alternating states similar to REM and non-REM. If confirmed, this would mean that dreaming and active rest are far older than once believed, stretching back hundreds of millions of years. Cephalopods take this to dramatic levels, octopuses flashing colors in REM-like phases, perhaps replaying hunts or encounters. The diversity of dreaming suggests it is not a quirk but a core function of rest. Predators and prey illustrate another contrast. Lions, secure in dominance, sprawl for 20 hours, conserving energy after intense hunts. Elephants, despite their size, sleep little, forced to travel for food and water while staying vigilant. Giraffes nap for minutes, often standing, always ready to flee. Koalas and sloths, with slow metabolisms and nutrient-poor diets, rest most of the day. Each species balances the equation differently: energy gained versus energy conserved, vigilance versus vulnerability. Hibernation and torpor extend this balance across seasons. Ground squirrels lower body temperature to near freezing, surviving months with minimal food. Yet even in this state, they wake briefly to enter true sleep. Bears in dens slow their systems but stir occasionally, mothers giving birth mid-dormancy. Hummingbirds enter nightly torpor, bodies appearing lifeless until dawn. Frogs, snails, and lungfish estivate in dry seasons, waiting for rain. These strategies blur the lines between rest and survival shutdown, showing how flexible the concept of sleep truly is. At the smallest scales, insects reveal surprising patterns. Bees droop on flowers at night, antennae still, memories consolidating. Deprived of rest, they forget roots and fail at navigation. Fruit flies show rebound after deprivation, their simple nervous systems still requiring recovery. Even jellyfish, without brains, pulse less at night and show rebound when disturbed. These discoveries suggest that sleep is as ancient as life's first nervous systems. The universality of rest makes one thing clear. It is not weakness, not wasted time, but survival itself. The body heals, the brain cleans, the mind rehearses, the immune system strengthens. Deprive a creature of sleep and systems collapse. Allow it and life endures. Humans, too, are shaped by this truth. We imagine our sleep patterns unique, but in many ways they are echoes of the animal kingdom. The first night effect, where one hemisphere of our brain remains more alert in new places, resembles unihemispheric vigilance in birds and dolphins. Our dreams, replaying daily tasks and emotions, resemble rats rehearsing mazes and birds practicing songs. Our group sleep in ancient times mirrors meerkats in burrows or ducks in flocks. We are part of the same rhythm, not separate from it. Modern life, however, disrupts these rhythms. Artificial light confuses circadian systems. Noise fragments rest. Technology keeps us stimulated late into the night. Shift work forces irregular patterns. Jet lag scrambles internal clocks. The same problems extend to animals in cities. Birds sing earlier, bats avoid noise, insects circle lights. Even ecosystems are reshaped by our interference in rest cycles. Yet the resilience of sleep remains. Deprivation leads to rebound, systems demanding repayment. Priorities shift. If REM is missed, REM returns in force. If deep non-REM is lost, the brain slips into it quickly the next night. Sleep may bend, but it will not vanish. Evolution has made it too essential. The mysteries of rest continue to captivate science. Why do elephants thrive on 2 hours while koalas require 20? How do migrating birds recover from weeks of fragmented naps? What do octopuses see in their color-shifting dreams? Why does deprivation prove fatal? And why does dreaming persist across so many lineages? Each question opens doors into biology, evolution, and consciousness. Dreaming especially remains one of life's great enigmas. Dogs twitch in imagined hunts, cats paw invisible prey, rats replay mazes, birds sing in silence, octopuses paint shifting visions on their skin. Dreams may be practice, memory, emotion, or all three. Whatever their role, their universality argues for necessity. Evolution does not preserve waste. Dreams must matter deeply, even if we do not yet understand how. Social sleep adds one final layer. Meerkats rotating sentinels, baboons roosting by hierarchy, chimpanzees weaving nests, dolphins resting in pods, bats clustering in caves. All show that rest is not only individual but collective. Safety, warmth, and bonds grow in the stillness. Humans, too, carry echoes of this heritage. Group rest likely shaped our evolution, allowing deeper sleep and perhaps richer dreams. When we step back, the lesson is clear. Sleep is not silence. It is action hidden within stillness, repair, rehearsal, connection. Every creature, from the simplest jellyfish to the most complex primate, must surrender to it. Its forms differ, but its purpose unites. At night, across deserts, oceans, forests, and skies, the world breathes in unison. Whales drift, birds perch, elephants doze, bees cling, humans dream. Each in its own way, all bound by the same rhythm. Sleep is not an interruption of life. It is life's most essential expression. The story of sleep, after all its strange shapes and endless variations, brings us back to one central truth. Every living creature must rest. It may look different in each species. Seconds of drifting naps in a bird, months of dormancy in a bear, twitching dreams in a dog, or flashing colors in an octopus. But the need is always there. Sleep is life's hidden rhythm, pulsing across the planet in silence. What makes it so fascinating is not only its universality but its creativity. No two species solve the problem in the same way. Giraffes manage with minutes, while koalas surrender for nearly an entire day. Whales rest with half their brains, while hummingbirds nearly shut down entirely at night. Bees droop motionless on flowers, while penguins snatch hundreds of naps in polar light. Each solution reflects a balance between energy and danger, memory and safety, feeding and healing. Predation risk has sculpted many of these adaptations. Prey cannot sleep deeply for long, so they nap lightly, ready to flee. Predators, safe in strength, indulge in long stretches after hunts. Yet even predators with dominance must eventually surrender to stillness, because no strength can replace sleep's invisible work. The functions of rest explain why it cannot be lost. In deep non-REM, growth hormones surge, tissues repair, immunity strengthens, and the brain cleans itself. In REM, memories consolidate, emotions regulate, and dreams unfold. Deprive an animal of rest and systems collapse. Rats die, birds lose songs, bees forget roots, humans hallucinate. Sleep debt may be postponed for days or weeks, but it always demands repayment. Life without rest is impossible. Dreams add a mysterious dimension. Dogs bark softly in their sleep. Cats flex claws, rats replay mazes, birds practice songs, lizards flick eyes, octopuses flash patterns as though reliving hunts. What they experience we cannot know, but the evidence suggests dreams are practice, memory, and emotional rehearsal. Evolution would not preserve them unless they mattered. Across species, they appear essential, perhaps even a foundation of intelligence. The universality of dreaming suggests it is ancient. If reptiles, mammals, birds, and cephalopods all display REM-like states, the roots must reach back hundreds of millions of years. Even simple insects show sleep-like rest that affects memory. Jellyfish without brains pulse less at night and rebound when deprived. Rest and dreaming may be as old as the first nervous systems, a survival tool shaped at life's dawn. Social life adds another layer. Many animals rest together, meerkats in burrows, ducks in flocks, bats in caves, dolphins in pods, primates in trees. Group sleep provides warmth, safety, and trust. Even in slumber, society continues. Humans carry echoes of this heritage. For most of history, we slept in groups around fires, rotating watchfulness. Modern solitary bedrooms are unusual in the scale of evolution. Our tendency to wake easily in new places or to sleep lightly on the first night may be ancient vigilance resurfacing. Circadian rhythms anchor these patterns. Light, tides, temperature, and social cues guide cycles. In polar regions, animals adapt to endless days or nights. In caves, rhythms drift without cues. In cities, artificial light disrupts natural timing, yet the need for rest remains. Rhythms may shift, fragment, or stretch, but sleep itself cannot be erased. Technology has revealed much of this hidden world. EEG sensors on wild animals show sleep in flight, rest in migration, and REM in reptiles. Cameras capture whales drifting vertically, bats clustered by the millions, and octopuses dreaming in colors. Each discovery expands our vision, proving that sleep is as varied as life itself. Yet questions linger. How do elephants thrive with so little REM? How do whales dream with only half their brains? What visions do octopuses replay in their flashing skins? Why do some species condense all benefits into short bursts, while others need long hours? Science is only beginning to unravel these mysteries. What we know is enough to change how we see sleep. It is not wasted time. It is not weakness. It is the quiet force that sustains life. Every night across Earth it repairs, rehearses, strengthens, and cleanses. It ties us to every other creature, dogs, birds, whales, bees, even jellyfish. When we sleep, we join the same rhythm that has carried life for billions of years. In the stillness of night, the world is alive with rest. Lions sprawl in grasslands, giraffes doze standing, whales float in seas, penguins nap in colonies, elephants pause for moments beneath stars. Bees cling to blossoms, bats cluster in caves, dolphins drift in pods, humans close their eyes. Together they breathe in unison, part of the same great cycle. Sleep is not an interruption of life. It is life itself, hidden, mysterious, essential. It is the bond that unites the living world, the silence that sustains the noise of day, the pause that makes survival possible. In every twitching paw, every shifting wing, every drifting whale, and every human dream, it whispers the same truth. To rest is to endure, and to sleep is to live.